Here we look at the graph of tan theta. So let's look at the basic graph y equal to tan x. And it's very different to the graph of sine x and cos x. What we immediately notice is that there is no amplitude for the graph of y equal to tan x. And in fact, the range of that is all real numbers, because really this keeps going towards our asymptote, but never crosses, of course, but gets closer and closer and closer. So our range in both directions goes towards negative infinity and positive infinity. And so that brings us to the fact that there are actually asymptotes in our tan graph. And at those particular values, pi on 2, 3 pi on 2, 5 pi on 2, tan does not exist. And therefore, that is why we have asymptotes. And we can see here that the asymptotes are plus or minus pi on 2. Now, we'll look at the general case in a minute. But the other thing that we can see here, that the graph repeats itself every pi. So for a tan graph, not your general one necessarily, the period of the graph is pi on n. And we've talked about what n is before. So if we had tan of 2x, then the period would be pi on 2. So it would repeat itself every pi on 2. We've already talked about the fact that the range is all real numbers. And of course, therefore, there's no amplitude. The asymptotes, okay, again, we can get the asymptotes now from the actual equation, because the asymptotes are plus or minus pi on 2n. Very important there, plus or minus pi on 2n. Here's a formula that we sometimes use for the asymptotes. X is equal to 2k plus 1 times n over 2n. Now k is just an integer, so 1 or minus 1, 2 minus 2, and so on. And the last thing there is finding the axes intercepts. And we can find them by using that formula. X is equal to k times pi on n. Now, a lot of this becomes natural when you look at the equation, and things will follow on from each other. So let's have a look at some of those examples. As per usual, when we're sketching a graph, we'll start off by talking about the trend, so we have in our mind at least an idea of what the graph should look like. So here there is no reflection, because the trend really does depend on the reflections, doesn't it? So we are basically going to have a graph that looks like that. Looks like a bit of a cubic, doesn't it? But it's not. So that's the trend of my graph. Now, with these circular function graphs, we used to find the amplitude, but of course we know now that there is no amplitude for a tan graph, so it wouldn't matter if there was a number there. Our range would still always be real numbers. We find the period. Now, for sine and cos, it was 2 pi on n. The period for a tan graph is pi on n. And you can see here that our n value is 2. So here, the period is pi over 2. We can also work out our asymptotes, and they're pretty important in helping us draw the graph. So we know the asymptotes is plus or minus pi on 2n. So in this case, because n is 2, our asymptotes are at plus or minus pi on 4. So we start to do our graph. We should always put our asymptotes in first. Now this doesn't ask us to do it between any domain, so I'll just do as many cycles as what I can actually do. So there's one lot of asymptote. Now to get my next lot of asymptotes, what I really need to do is add the period onto my asymptote, my last asymptote there. So I've got pi on 4. So then my next asymptote would be plus pi on 2, and pi on 2 is 2 pi on 4. So really, my next asymptote is at 3 pi on 4. So really, the asymptotes are the period apart. And so if I go up another 2 pi on 4, I would be at 5 pi on 4. Another 2 pi on 4, I would be on 7 pi on 4. So that is how I then keep going with my asymptotes. I could go in the other direction, but I haven't got anything on my graph there, so I'm not going to do that. So now we know that our trend is positive, that our graph is between those asymptotes and oscillates around the middle because there are no translations. So let's have a look there. Okay, I'm going to try and make it look like it's getting as close to my asymptote as possible. Okay, it's going to go through pi on 2 there and going down that way. Again, it's going to go through there and going through there. That's why using a pencil is probably your best bet here. A nice steady hand to get a nice looking graph and get full marks for it. Okay, so don't ever let it look like your graph is going to cut those asymptotes because you will lose marks. They need to go towards your asymptote. Okay, and we should also really label those asymptotes. So x is equal to pi on 4. X is equal to 3 pi on 4. X is equal to 5 pi on 4. X is equal to 7 pi on 4. And over here, x is equal to minus pi on 4. And if I was going to keep going and fill out my whole graph, then I could actually have my graph going to there if I wanted to. It really didn't state what the domain was, so I've done 1, 2, 3, 4.5 cycles of tan 2x there. Solving tan x is like solving sine x and cos x. We're going to use exactly the same method as what we did for those two. Now here you can see that our domain is between minus pi and pi. So let's start off by looking at where our solutions will be. And we know we're dealing with a minus 1 here. So where is tan negative if I go around to pi? And it would be negative in the second quadrant. If I go this way to negative pi, where is tan negative? It's negative in the fourth quadrant. Okay, so there where my two solutions are going to be. So let's start with the basic angle. Basic angle, tan x, and remember we only want something in the first quadrant, so tan x is equal to 1, and we know that when tan x is equal to 1, x is equal to pi on 4. Now, is that a solution that I am going to accept? And no, I don't want anything in that first quadrant, but I do want something in the second quadrant, which would be pi minus pi on 4. All right, that's going in that direction. If I go in the negative direction, that's negative theta, isn't it? Remember what we talked about? That was negative theta, so it was pi minus theta negative, pi plus theta negative, and 2 pi minus theta negative. So here we're in that first quadrant but going in the opposite direction, so it's negative pi on 4. So my final answer there, if I put them in order, negative pi on 4 is the smallest value. Pi minus pi on 4 is 3 pi on 4. So they are my solutions between negative pi and pi. So basically what we're talking about is where y equal to negative 1 cuts the graph of tan x. Let's keep going with the next one and we'll talk about where our solutions are for this one. Now, this time we have 2x, which means that we knew before that x was between minus pi and pi, and it was including both of them. So now 2x is between minus 2 pi and 2 pi. Don't forget to change that domain. So if we're going to go all the way around, all seeing that's in one direction, and if we go the other direction, we're going to have ones going in the same spot but going backwards. So let's now work out what our basic angle is. Remember, we don't want to talk about double angles when we're talking basic, so tan x is equal to root 3. And when tan x is equal to root 3, we know that x is equal to pi on 3. Now, is that a solution? Well, in this case, it is, because our solution was there and there. So 2x is equal to pi on 3, and the next one is going to be pi plus pi on 3. Going in the negative direction, I'm going to have minus pi on 3, and because that's that one there, and here I've got one in this quadrant which is minus 2 pi minus pi on 3. Let's start tidying that up, and we get 2x is equal to pi on 3. Pi plus pi on 3 is 4 pi on 3. And then pi minus pi on 3 is 2 pi on 3, so it's a negative 2 pi on 3. And the last one here is negative 2 pi minus pi on 3. 6 minus 1 is 5 pi on 3, so it's negative 5 pi on 3. Okay, let's make some room there so that we can now tidy up our answer even further. We've got 2x there and we want x, so x is going to be pi on 6, 4 pi on 6, minus 2 pi on 6, minus 5 pi on 6. And I'm going to write them in order and simplify them as well. So what is the smallest value there? Obviously minus 5 pi on 6. So that's my first one, followed by minus 2 pi on 6, which is minus pi on 3, followed by pi on 6, and then followed by 2 pi on 3. So they are my 4 solutions there. Now the next one's a little bit unusual. Have a look at this. 2 tan 3x is equal to 0. Again, between negative pi and pi, but our domain has been stretched. So 3x is between negative 3 pi and positive 3 pi. We do need to change our equation here and get rid of that 2. So we've got tan 3x is equal to 0 divided by 2, which is still 0. Now, if you think about this in terms of your basic angle, okay, so tan x is equal to 0. Where is tan x equal to 0? Well, it is actually on the quadrant. It's not in a quadrant. So if we go around to 3 pi in the positive direction, we are really only going to have 3x equal to 0 as our first solution, and then 2 pi on our next rotation. If we go around again, 4 pi is too big. How about going in the opposite direction? Well, again, we start at 0 and we go to negative 2 pi, and negative 4 pi again would be too big. So we don't want 3x though, we want x. So 0 divided by 3 is 0, 2 pi on 3, negative 2 pi on 3. And I like to write them in order. So negative 2 pi on 3 is the smallest there. 0 is next, followed by 2 pi on 3. So there are three solutions, I should say, between negative pi and pi for the equation 2 tan 3x equals 0. So we do have to be a little bit careful. They are done differently when our first solution is on the boundary, not in the quadrant.